Hello, everyone. My name is Joel Pepper, and I'm going to be presenting our work from analog records to computational research data, building the AI-ready lab notebook, which is a collaboration between Metadata Research Center at Drexel and the Reticular Synthesis and Material Design Lab at University of Central Florida as part of the NSF-sponsored Institute for Data-Driven Dynamical Design. A bit of background. The practice of scientific note-taking dates back to antiquity, with paper lab notebooks remaining a staple in laboratories today. Electronic lab notebooks represent a significant shift in how research is recorded, providing boosts in archival integrity, standardization, and data retention, but they're often impractical to use in the middle of bench work when, for example, one is wearing gloves or working with potentially dangerous substances. As such, chemistry and other labs often accumulate stacks of paper lab notebooks that remain completely undigitized, their contents largely inaccessible for any sort of large-scale study. So these notebooks, produced over many years by many different researchers, may in aggregate have the potential to provide new insights into the successes, failures, and pedagogy of laboratory research. Um, when labs do not digitize their old lab notebooks in any way, they become quote unquote data at risk. But the onerousness of retyping notebooks into an ELN leads many experimentalists to forgo using them. Thus, research is needed to improve the ease of converting paper lab notebooks into digital, quote unquote, AI-ready archival records suitable for analysis at scale by modern machine learning techniques. So kind of the overarching goal for this project is to advance methods for converting scanned handwritten notebooks into structured, fair, AI-ready data. Kind of three major aspects of achieving this goal are to extract the archival data from notebook page elements such as tables and text blocks to support computational analysis of these analog artifacts, to identify common error patterns in the extraction outputs and build an automated post-processing pipeline to correct them, and finally to actually use this extracted AI-ready data to perform document classification and clustering analysis to try to answer scientific questions about experimental design, outcomes, and/or student learning. This study utilizes a collection of roughly 80 lab notebooks focused on metal organic framework crystal synthesis produced by the Reticular Synthesis and Material Design Lab at UCF's starting from around 2013. The notebooks consist primarily of reaction diagrams, tables, text blocks describing the protocol, as well as some additional diagrams specific to the given experiment. I have a few examples on this page of these lab notebook pages from four different authors. Certainly varieties in the style and even the page composition a bit, but for the most part, they follow a consistent structure of having a reaction equation at the top, followed by a table describing the quantitative values being used in the protocol, text block describing the protocol itself, and sometimes an additional table or diagram at the bottom. Kind of the methodology outline for this project is roughly as follows. Extract the content from pages via optical character recognition. Kind of example of that shown here for this text block, and more on that in subsequent slides. Uh, Post-process the output to improve accuracy and ideally flag detected but potentially uncorrected issues for manual review. For this table, the OCR output looks something like this, which, just to give one example, these slashes for empty records kind of can get read as slashes or ones or whatnot, something that has to be dealt with. This header has some extraneous characters in it, etc. We want it to look more like this down here at the bottom. Number three, build an archive that can be presented by, or at least in the style of an electronic lab notebook. Kind of have a mock-up of what that might look like here with, the process pages on one side and kind of the extracted contents viewable in these tabs here. And kind of current work in progress, work to further bolster the AI readiness of the data by tokenizing the protocols into kind of sequential lists of actions paired with associated attributes. So, got another slide on this, but that's kind of the general structure of what I'm talking about there. Um, Okay, so in terms of content extraction, recently the capabilities and performance of document content extraction software have rapidly increased. This figure from a November publication shows the quantity of new releases within this niche since just June of this year. Much of this rapid growth has been enabled by vision language models, which leverage LLMs for tasks such as OCR by encoding images into prompt-like structures that are compatible with the language models, as was discussed in one of our previous presentations. Um, so we, for this work specifically, are in the process of switching our work over to using one of these newer tools called OM OCR2, which is an open source tool released just in late October, so just a little bit before we were kind of writing up this submission. Um, but previously, we were using a two-step process for content extraction involving both the Tectron 2, which is somewhat older image segmentation toolkit, and a commercial OCR tool called handwriting OCR. Back before the big proliferation of these vision language models, handwriting OCR was chosen as it supports extracting tables directly to um, comma separated value format, a feature many other OCR packages lacked. Ulm OCR2 removes the need to segment pages before even running the OCR. Its default output is an HTML document containing all the different types of content found on the page, including tables and equations. It provides a significant increase in ease of use, accuracy, and compared to handwriting OCR and other proprietary cloud-based tools, affordability. So you can kind of see on the left here, this is sort of an output from Tectron 2, the first step of our original kind of pipeline where we'd actually segment the page into text blocks and the table and the reaction uh, equation here, which still has its use from an archival and, uh, processing standpoint, but these newer very, as far as I'm concerned, advanced vision language model tools that's wholly unnecessary. If I put in this page without doing anything to it, get HTML out, including even like the headers equation, it's formatted as a table. Can handle all that. Um, But regardless of the extraction method, there will always be some amount of errors in this outputted data. Inconsistent and well-structured lab recording standards can allow for automated correction of many OCR mistakes by leveraging domain knowledge about the document's contents to double check the value of each cell within a table. To give one example. Um, Checks for the tables in the RSMDL lab notebook, which follow a pretty strict composition standard and guidelines, include removing any empty rows or columns and realigning elements. This is something that was often generated by handwriting OCR, just as, just a kind of mistake it like to make. Although OCR2 does not seem to exhibit this issue really at all. Correct basic kind of header errors, such as reading FW formula weight as, say, MW or something to that effect, because we know kind of what headers to expect up here. Validating that numerical columns contain only numbers. In these tables, pretty much everything's a numerical column except for the reagent. Correctly handling slashed or blacked out cells. So you can see here, the researchers like to sometimes put crosses just to make it clear that this wasn't forgotten, it just wasn't used, but that can show up in the OCR and need dealt with when it's read as a slash or a one. And then in terms of the actual domain knowledge corrections, one of the big ones we can do with this kind of table is verifying that for each reagent, that the formula weight times the amount of moles we have equals the grams written in the table. And second kind of check of that nature is verifying for each column that the equivalency ratios listed in the EQ column hold true for the amount of moles listed in the millimoles column. And this form of redundancy in the tables is useful for a quick sanity check by chemists as they're working, but also unintentionally comes in very handy for bolstering the accuracy of our content extraction process. So what I mean by that is, since EQ here is 1 and EQ here is 1.7, this number times 1.7 should give us this number, and that can be used to get a vertical check on the table as well as the previously mentioned kind of horizontal check. So following the extraction and post-processing, an archive containing all the images from the notebooks as well as a JSON record of the extracted content is generated. The archives can be rendered in an ELN-like web interface or potentially, imported into a full-fledged ELN in the future. And again, I kind of showed this earlier, but this is kind of a mock-up I put together of what they might look like. So we have all the pages we've covered. Ideally, these might be grouped more by experiments, not just by pages, because sometimes the experiments can span more than one page. But based on what we're extracting now, have kind of three tabs for the segmentation done by Detectron 2, the table processing, and the text processing, which isn't shown for space. So due to the very recent release of OLM OCR2 at the time we were writing our manuscript, we, for results evaluation, used a limited sampling of 30 notebook pages to compare the performance of our original Detectron 2 and handwriting OCR process to OLM OCR2, as well as evaluate the performance of our post-processing script. Including the table headers, this sampling of pages contains 1,092 total cells. So going through this table here, handwriting OCR alone made mistakes such as giving an incorrect number or swapping the location of a value in 199 of the 1,092 cells for an error rate of about 18.2%. Almost CR2 made 61 mistakes for a 5.59% error rate, representing just a huge out-of-the-box performance improvement. If we apply our post-processing fixes to the original handwriting OCR2 or OCR method, we can get that down to just 62 mistakes for a 4.76% error rate, an improvement over just the default output of 73.87%. And if we apply the post-processing to OLM-OCR2, can drop that down to 46 mistakes for a 4.21% error rate, an improvement of 24.69%. So there certainly is still some room for improving our post-processing, especially in terms of adapting it more specifically for almost CR2, which is something that is ongoing. With the core kind of automated archival aspects of this project largely completed, we're now working on converting the contents of text blocks into a tokenized list of actions. Connecting actions with any entities, durations, temperatures, and sizing information associated with them. This work is an extension of previous work by our group using LLMs to similarly tokenize methodology sections from MOF research papers instead of lab notebooks. So a little more straightforward in that case, just working with a paragraph or a few paragraphs, but similar technique can be applied. Tokenizing protocols in this manner can greatly improve machine learning analyses of their contents, thus increasing the data's AI readiness and the potential for scientific knowledge discovery. Once tokenization and rectification, once tokenized and rectified with quantitative data found in the tables, we plan to begin analyzing these notebook records more deeply in order to search for novel insights into moth experimental design and the pedagogy of moth synthesis. The chemists we're working with have some interesting directions they want to take that in terms of things, patterns that might be hidden in their lab notebooks. Um, Okay, so finishing up, to restate a bit, the overall goal of this project are to make data contained in paper lab notebooks AI ready, and to mine information in these notebooks for scientific insights. The content extraction aspects of the work are now largely completed, with some potential remaining to further lower output rates. And kind of as an aside related to this part of the project, something that bears repeating is the incredible pace of advancement on document processing and extraction tools that occurred this year alone, which serves as a lesson on how critical it is, even if it's not always easy, now in the AI age, to stay on top of the latest advancements in really any sort of machine learning tools one is using, given how quickly technology can radically change. And then finally, work to tokenize and further process the digital notebook archives. To bolster their AI readiness is ongoing, with an eye towards using the notebooks to answer scientific questions. And yeah, that's all I got. So I think maybe